welcome you to the 48th Oppenheimer Memorial Lecture, A Brief History of Black Holes, From Oppenheimer to LIGO, featuring Professor Kip Thorne. We are very honored to have Professor Thorne here tonight. He comes to us from the California Institute of Technology as the Feynman Professor of Theoretical Physics and as a 2017 Nobel Prize laureate in physics. Professor Thorne continues the committee's long tradition of hosting exceptional and distinguished speakers such as Hans Bethe, Linus Pauling, James Watson, and Sir Paul Nurse. The committee takes great pride in hosting this lecture series and in awarding scholarships to outstanding seniors in the local area. This year, our winners include Los Alamos High School seniors Jonathan Dorn, Christopher Coe, Amanda Lee, Joseph Sorrell, Sonia Williams, and Stephen Zhao. Our regional winners include Ariana Garcia and Elizabeth Walker from Capitol High School, and Taylor Roybal and Noelia Topete from Milwaukee Valley. This evening, the committee is honored to have the new director of Los Alamos National Laboratory, Tom Mason, here with us to provide the introductory remarks for our distinguished speaker. At this time, please join me in welcoming Tom Mason.
Thank you, Allison, and I'd like to thank the Robert Oppenheimer Memorial Committee for the work that they do to honor the legacy and memory of the founding director of Los Alamos, both through the scholarships and this public lecture. It's my great pleasure to introduce tonight's speaker. I'm not going to read the whole biography because it's in your handout, but I would like to point out that there are many ways that a physicist, a scientist, can contribute. And I think one of the really unusual things about Kip Thorne is he has made major contributions in every avenue of endeavor. Of course, he's been recognized with the Nobel Prize in Physics in 2017 for his contributions to the experimental discovery of gravitational waves, LIGO. That was a remarkable and exciting announcement, but the thing that can get lost in the excitement of announcement of a new discovery is the very, very long journey that it took to get to that point, and the tremendous commitment and persistence that was taken on part of that group to pursue something which at the outset was really kind of pushing the envelope in terms of feasibility. And in fact, it took a lot of courage, I think, to follow that through, because the initial incarnation of LIGO, if it worked as well as it possibly could, the most likely outcome is that it would not see anything. However, in doing that, enough was learned to allow the development of something called advanced LIGO, which, if it worked as well as it possibly could, would see something. And that was the result that was recognized in the 2017 Nobel Prize in Physics. But it's not just the research contributions. Kip Thorne has also supervised 52 PhD students who have gone on to make major contributions in a variety of different endeavors. Obviously, in the pursuit of science and academic careers, but in business, in government, and even here at Los Alamos. And that's another major legacy that any, I think, scientist can be proud of. But in addition to those contributions to our understanding of the universe and the development of the next generation of physicists, he's also been really very active in the communication of science through some of the traditional means with things like textbooks that have become widely adopted, but also into popular culture and his contributions to Hollywood. Of course, it helps being at Caltech because you're sort of close by. And so I think this is really the measure of an extraordinarily well-rounded career, and something that I think is something that probably brings a lot of you here as well. The topic for today's lecture really couldn't be better suited to the individual that we're honoring, because if you look at the journey from the beginning of the idea of black holes and the role that Oppenheimer played during his days as a Berkeley professor, active in research, to the discovery that was realized in 2017. There's a great linkage between that proud history that we're celebrating and some of the most exciting science that's being done today. So please join me in welcoming tonight's lecture for the J. Robert Oppenheimer Memorial, Kip Thorne.
Thank you, Tom, for that embarrassingly effusive introduction. So J. Robert Oppenheimer was one of my heroes. And as a result, when I was invited to give this lecture, there was no way I could possibly say no. And so here I am. I knew Oppenheimer when I was a graduate student at Princeton. This is me in those days, 1962 to 1966. And this is Oppenheimer in that era, 62 to 66. He was the director of the Institute for Advanced Study. That's where he had gone after he was here at Los Alamos. And my introduction to him as an intellectual giant came as a result of the fact that it was only about a 20-minute walk from my office to the Institute of Advanced Study, and they often had really interesting seminars. So I would go over for the seminars, and Oppenheimer would sit there in the front row with his pipe in his mouth, typically no smoke in it, he just liked holding it in his mouth. And it didn't matter what the topic of the seminar was, whether it was relativity or nuclear physics or astrophysics or what we in those days called solid state physics, condensed matter physics, any area, sub-area of physics. Those are the only ones I went to. I don't know how he was on economics. But there would often come a moment in the lecture when the lecturer was having trouble explaining himself to the audience. And when that became obvious, Oppenheimer would stand up, he would take his pipe out of his mouth, and he would say very succinctly, what the lecturer is trying to say is. And he would explain it in a totally understandable way. And as I say, it didn't matter what the topic was. And this was a true tour de force that I so admired. So I came to appreciate both his communication skills, but also his remarkable intellect. Now, when I went to Caltech as a professor later on in the 1960s, I built a large research group, rather similar to the research group that Robert Oppenheimer had in the 1930s when he was spending about 2/3 of the year at Berkeley and 1/3 at Caltech. And I knew from friends who had been in Oppenheimer's group as students or postdocs how Oppenheimer operated. He would come in every day and he would set the whole group down around himself and he would ask each one to explain what that person had thought of or done in the preceding day. And for an hour or two, there would be a round robin of discussion. And I thought that was absolutely wonderful, except I didn't see how I could do it every day, so we did it once a week. But basically, I patterned the structure of my research group after Oppenheimer's research group. This was also part of my admiration about Oppenheimer. And so this is Oppenheimer in that era, and when he was at UC Berkeley and Caltech. Now, let me turn to Oppenheimer's contribution to the concept of black holes, 1938-39, just before World War II. The big question in that era, in the late 1930s, is what happens to a star when it dies? That is, when it exhausts the nuclear fuel that is keeping it hot so it remains very big and puffed out. When the nuclear fuel is exhausted, it has to shrink. And what does it shrink to become? And there were two answers known in the late 1930s. One of the answers had come largely from Chandrasekhar in 1930. He had said that the star could shrink down and become what we call a white dwarf. A white dwarf with where you take the star originally has a size of 1 million kilometers, shrinks down to about the size of the Earth, 10,000 kilometers in size. Then it just rests there and slowly cools off and dies. A second answer came from Fritz Zwicky in 1934 when he postulated, without any strong physical, I think, understanding even, but enough that his tremendous intuition told him that there was also a possibility that you could form what Fritz Zwicky he coined the phrase, a neutron star. So you shrink from the size of a white dwarf on down to a size of 20 kilometers. That's not much larger than Los Alamos. And you still have a star that weighs, say, as much as the sun weighs, but it's now shrunk down, so it's basically made of pure nuclear matter. And the key issue that we came to that Chandrasekhar discovered was that no white dwarf could be heavier than about 1.4 times the mass of the sun. And so there was a big question as to how heavy can neutron stars be, and that was one issue that Oppenheimer set out to answer, and he answered together with his student Georg Volkov in 1938. They did a detailed analysis using the properties of nuclear matter as it was understood at that time, analysis of the structure and masses and radii of these neutron stars, and found that neutron stars could be no heavier than about 1 solar mass. Today, with a much better understanding of nuclear physics, we know that that number is really something like 2 or 3 solar masses, but still there's a maximum mass for neutron stars and for white dwarfs, and that then led to the question is, what happens to a star that is heavier than that when it dies? And this was then the question that Robert Oppenheimer, together with a second student of his, Hartland Snyder, who, by the way, had been a truck driver in Utah, where I grew up. But this was a few years before I grew up, before he went to work with Oppenheimer. So Oppenheimer and Snyder then did a detailed mathematical analysis using Einstein's relativity theory, because it was clear that relativity would be very important inside these objects, that space and time would be curved, warped inside these objects. So they had to use the equations of general relativity to analyze this. And so what they did was they imagined a star that didn't have any pressure inside itself. Of course, all stars have pressure, but they were thinking about a star that was so heavy that they knew that the kinds of forces that support a white dwarf and a neutron star could not beat out gravity, so gravity would just overwhelm them. So they pretended there was no pressure at all and just analyzed what happened as that star shrank smaller and smaller, smaller and smaller and smaller. And ultimately, they found that it became so small that gravity was so strong that nothing could get out from inside the star into the external universe, and time at the surface of the star slowed to a halt. It stopped flowing. Now, this was truly strange, really weird. In the words of Oppenheimer, the star cuts itself off from the rest of the universe. This was really very puzzling to everybody else. I think Oppenheimer felt comfortable with it. He'd done the mathematics. It was very clear that that was what was going on. As Yevgeny Lifshitz, a Russian friend of mine, 30 years later said to me, explaining how he and his friends in Moscow saw this when they read the paper that Oppenheimer and Snyder wrote about this, he said to me, "You cannot appreciate how difficult it was for the human mind to understand this." John Wheeler, who was my PhD mentor at Princeton, he fought against this prediction. It just did not make physical sense. He didn't see how it could possibly be true from 1953 to 1962. And then as a result of new ways to think about the calculation that Oppenheimer and Snyder had done, new ways to describe it mathematically, new ways to understand it physically, he suddenly came to embrace this prediction, and he even gave the name to this object that's left behind, that's cut off from the rest of the universe that we all use today. He called it a black hole. And so finally then, beginning about the time that I arrived at Princeton, black holes were on the scene. Now, I'm not going to tell you the subsequent history. It's a very fascinating history. Large numbers of people contributed to it. I do tell the story in my book, Black Holes and Time Warps, which should be accessible to everybody in the audience. So I welcome you to go buy a copy, but it's very old. It's somewhat out of date, but it's up to date, up to about the time that I published it, which was in the early 1990s. What I want to do now for the next little while is explain what we understand today about quiescent black holes. That is, black holes that are just sitting there, not doing anything, not pulsating, not colliding with other black holes, just sitting quietly. We know today that there are about 10 million such black holes in our Milky Way galaxy. And there are a billion, that's 10 to the 18, in the entire universe. That's an unbelievably large number of black holes. We know that their masses range from a few times the mass of the sun up to 20 billion times the mass of the sun. The largest one that's currently known is about 16 billion times the mass of the sun. Their diameters range from about 10 kilometers to about 100 billion kilometers. Their diameters are proportional to their masses. So this is a huge range of black hole sizes and masses, an enormous number of them in the universe that we know from astronomers actually having taken a census of black holes through various kinds of observations over the period since Oppenheimer did his original work. Now, what is a black hole? A black hole is made from warped space and time. And I can explain this to you by telling you that the diameter of a black hole is far larger than its circumference. And you look at that and say, well, that's obviously not true. There's no way that can be true. But it is true because the black hole is made in part from warped space. And you can understand it in this way. Imagine taking a child's trampoline, a sheet of rubber, put it up on high stilts, and then put a very heavy rock in the center so that it bends down like that. And if you're an ant, you're a blind ant, and you go marching around this circumference, and you measure the circumference, you can then go and measure the diameter, and you go marching around and around and around, and obviously the diameter is far larger than the circumference, and you say to yourself, because you have worked at Los Alamos, you're a really smart ant, you say it's obvious that the reason that the diameter is big compared to the circumference is because the space in which I live is warped. And you and I can see why it's warped. It's because it's a bent sheet of rubber. Precisely the same diagram applies to a black hole. If I take an equatorial slice through the black hole, so you would have thought that was a two-dimensional surface, flat like the surface of this podium. It's not. It's warped in precisely the same way as that rubber membrane was warped. But it's warped in a higher dimension. In the movie Interstellar that I worked on, it's called the fifth dimension because we have three dimensions we're familiar with, north, south, east, west, and up, down. Time is a fourth dimension, and the fifth dimension is the dimension in which this warping occurs. Okay. And so that is, and in the place of the rock down at the center, there's something called a singularity that I will not go into, but it's a place where the laws of physics break down. The laws of physics as we know them, and a new set of physical laws called the laws of quantum gravity take over. And these are the same laws as govern the birth of the universe, and they govern whether or not you can make a time machine for going backward in time if you're an extremely advanced civilization. So they're very important laws that we need to understand. One of the reasons is to understand the centers of black holes, but I'm not going to go into that. Now, the black hole, the aspect of black holes that's familiar to everybody is that if I fall into the black hole, sending signals to you, say microwave signals off a little microwave antenna, when I go below the surface of the black hole, which is called the horizon, as I keep falling in, the microwave signals fall in with me. They cannot get back out. And so that's the key thing about black holes, that anything that falls into it can never get back out, cannot send any signals back out. Now, time is also warped inside a black hole, in the vicinity of a black hole. As you go down near the horizon and you hover there, time slows to a halt right at the horizon, as I told you before. And what happens if you're inside the black hole? I mean, what is slower than a stopped time? Time flows in a direction you would have thought was a space direction. It flows down toward the singularity. And because nothing can move backward against the local flow of time, everything that falls inside the black hole is pulled inexorably by the flow of time down to the singularity and destroyed. And so that's not, in order for you to explore the interior of a black hole, you have to fall in and pay the ultimate price that you can't publish the results that you, that you got, but you also pay the ultimate price of your life, probably. There's a little caveat about that, probably. It's conceivable that you can survive. And that goes to something else that I've been involved in that I invite you to do. Go look at the movie Interstellar and read my book, The Science of Interstellar. And you can find out about the fact that there may be gentle singularities inside there too, which you may be able to survive, and plays a role in that movie. But let me focus on the exterior of the black hole. Black holes generally spin on their axes like the Earth does. And in spinning, they drag space into a whirling motion like the whirling motion of the air in a tornado. It's very fast near the horizon of the black hole, slow farther away. So I'm now going to show you a precise map of the warped space-time of a non-spinning black hole. The horizon is down here at the bottom. It looks like a circle, but that's because I removed one space dimension. If I restore that space dimension that I removed, then it's a flattened sphere. The color coding is the slowing of time as you near the horizon, where it's yellow, time flows at 10% of the rate that it does far away. Time is halted at the horizon. And then the question comes, what warps the space and the time of a black hole? And the answer is, it's the energy contained in the warping. Now think about that. In order to bend the string of a bow, you pull back, the bow itself bends and the string bends, and you're putting a lot of energy into the wood and into the string as you pull back. So there's a lot of energy put in there as you produce the warping. Similarly then, in warped space-time of a black hole, there's a huge amount of energy, and it is that energy that that produces the warping. The warping is sustained by the gravity or by the space-time warping of its own energy. It's what we might call a gravitational soliton, an object that holds itself together by its own self-interaction. Now this is a drawing now of a fast-spinning black hole, and now you see the throat to the black hole, as seen from the higher dimension, stretches down a lot farther, and you see the arrows that indicate the dragging of space into whirling motion are very precisely laid out there. It's a fast angular velocity of motion near the horizon, much slower farther away. Now, because the whirling motion is faster near the horizon and slower farther away, that means that if I put my wife here just above the horizon, hanging or falling in, it doesn't matter, her feet are dragged around in a whirling motion faster than her head. And so if she looks down, her head looks down at her feet, her head sees her feet going around very fast clockwise, and her feet see her head whirling around very fast clockwise. It's like taking a wet towel and wringing water out of it. If your right hand is turning clockwise as seen by your left hand, then your left hand is turning clockwise as seen by your right hand. So there's a clockwise twist of the towel. Here there's a clockwise twist of space. We think of this as a vortex of, this says counterclockwise, but I usually use counterclockwise in red. I've screwed up my standard convention on colors. Anyway, so there's a counterclockwise vortex sticking out of the black hole as a vortex of twisting space, and it's as real and as physical as my arm is sticking out of my body, but it's made from warped space and time. And there, at the south pole of the black hole, there is similarly a clockwise vortex. So there are two vortices sticking out of a black hole, one with clockwise twist and one with counterclockwise twist. And I'm going to return to those at the very end of my lecture because it's a really interesting question to ask. What happens to those vortices when black holes collide? So that's my promise, key thing toward the end of the lecture. Now, what does a black hole look like? So here I have a black hole as seen from the higher dimension. There's a camera in orbit about it. There's a star over here, and the star can send light to the black hole along that light ray. But another light ray can go around the black hole around the other side, being bent by the gravity and the warped space-time of the black hole. And another one can go down and go around the black hole once and come to the camera. There's a shadow here where no light rays can come in. And then there are a huge number of possible light rays that can bring then different images of the star. And so in this particular case, I'm just showing two of the images of that star, the image that comes along this light ray and the image that comes along that light ray. Here's the shadow of the black hole. This is what we call gravitational lensing, and it is producing many images of each star. Now, the team that I worked with on the movie Interstellar used the software that we created in order to make images make pieces of the visuals for Interstellar to compute precisely what it would look like to the camera as it moves around a fast-spinning black hole gradually in orbit. And you're now looking at the images of many, many stars, and it is quite a sight to behold. This thing here is called a gravitational it's called an Einstein ring. There's another Einstein ring down in here. In fact, a whole series of Einstein rings near the edge of the black hole. If you look carefully, you see images of one star created in pairs, and then an image will go along and it will annihilate against another image and disappear. So there's fantastic visual phenomena going on due to this gravitational lensing. But that's not the way the black hole looks in the movie Interstellar, because in the movie Interstellar, as in the real world, most black holes are surrounded by disks of hot gas. We call these accretion disks because the gas is going around and gradually accreting onto the black hole. And so where do those disks come from? They arise typically when a black hole tears apart a star that strays too close to it. And so here's a computer simulation showing that. There is a black hole that you can't really see just yet sitting up here inside this box. There's a star that is coming in and going to be torn apart by that black hole as it nears it. And watch what happens in this computer simulation. It whipped around the black hole, and it has been torn apart. It is trailing the guts, the interior of the black hole. Trailing the guts of the star. Is trailing out behind. And ultimately, a portion of the gas is caught around the black hole and forms the accretion disk. And much of the gas gets thrown off into interstellar space. Now, what do black holes look like if they have accretion disks? This is an image that was produced again by my friends who worked on the movie Interstellar with me. And the question is, how does it come about that the black hole looks like this, and why is this not quite the same as what you see in the movie Interstellar? So let me answer the first question. Suppose you have a camera here. You have this very flat accretion disk. In the movie Interstellar, it's a very thin disk. Light ray from the top back face of the disk goes over the black hole and is pulled down to the camera. So the camera thinks the top back face of the disk is up here. And so is it possible? No, it's probably not possible to turn that light down, but that's all right. So down here, good, thanks. So there's the top back face of the disk reaching up over the black hole due to this gravitational lensing. The bottom back face of the disk similarly sends light rays up to the camera here, and so you see the bottom back face of the disk down below the black hole. You see the shadow in here, and light rays come directly off the disk to the camera, and so you see this crossbar. Now that's not quite how it looks in the movie Interstellar. It looks like this. And the reason is that in the movie Interstellar, Christopher Nolan, the director, insisted on two things. First, that you see the black holes that would be seen not with a human eye, but as seen when filmed by an IMAX camera. I mean, he's a stickler for realism. The rest of the movie was filmed with an IMAX camera, so obviously this has to look like what it looked if it's seen by an IMAX camera. So the light rays went into the camera, and some of that light scattered off of the lenses in the camera and produced this glow all around. So that's due to scattering of light inside the camera. Second thing that is different is this looks red on that side and blue on this side, because this side the gas is moving toward you, and there's a Doppler shift making it look more blue and brighter. That side looks more red and dimmer as the gas is moving away from you. But Christopher Nolan said, look, we know that when the human eye looks at a very, very bright light, the human eye is incapable of distinguishing colors. So therefore, we will get rid of all the colors, and that's what was done in the movie Interstellar. So that shows you the level of realism. Now, I thought I had, just a second. I thought I had something more after that. No, I didn't yet, not quite yet. Okay, so at the center of our Milky Way galaxy, there's a very large black hole that weighs 4 million times as much as the sun. And Andrea Ghez and her research group at UCLA have been studying the orbits of stars around that black hole for the past 20 or 30 years. And this is a visualization of those stellar orbits. And it's quite interesting to watch. And you can guess where the black hole is. It's the location where stars go whipping around very, very quickly. So it's right in here. And so black holes are known not only observationally by their accretion disks, but also by their gravitational pull on the stars. And it's that gravitational pull that also enables us to weigh the black hole and see that this black hole weighs 4 million times as much as the sun does. Now, one of the great observational discoveries, though it required something like 15 years of effort by a large team, was the first observation of the shadow of a black hole's horizon by astronomers. And this was an observation made that hit the front pages of all the major newspapers about a month ago. It was done by a team called the Event Horizon Telescope team. What this team did was it worked with very, very short wavelength radio waves. Well, really millimeter wavelength, 1.3 millimeter waves. So very, very short wavelength in order to get high resolution. And collected data with a set of telescopes all around the world. And combined those data together to make an image coherently with all of the data superposed coherently. And that's the shortest wavelength with which current technology can do coherent superpositions of signals from all around the world. And so this was a very masterful effort by a team of about 400 scientists and engineers at about 100 institutions around the world, led by Shepard Dolan at the Harvard-Smithsonian Astrophysical Observatory. And the first success was in looking at the black hole in the galaxy M87, which is a giant elliptical galaxy not terribly far from us. And here is what the image looked like. Here is the black hole horizon, the shadow of the horizon. And here is a bright edge here that is where the gas is moving toward you, so it's blue, so it's made much more bright. You're not really seeing the shift in wavelength, you're just seeing the brightness in the way that this image was made. And from the size of the shadow, the conclusion was that this is a 6 billion solar mass black hole at the center of this galaxy, a gigantic black hole at the center of the galaxy. Now, it's interesting to compare the image in M87 and the image in the movie Interstellar. They're quite different. The key difference is you have this crossbar in the case of Interstellar, and you have the glow that I've already talked about, and you have lost the brightening due to the Doppler shift. The key difference, the absence of the crossbar, is due to the fact that in M87, the gas is it's optically thin, with only a small amount of gas between us and the horizon of the black hole. And so the shadow really shows through very strongly. But the gas glows quite strongly when you're looking through the much thicker layer of gas off to the side. And so it's just the difference in the flow of gas in the case of M87, in the case of the black hole gargantua in the movie Interstellar. I now want to turn to gravitational waves and LIGO and the most recent, then, insights into black holes that have come from LIGO. Albert Einstein predicted the existence of gravitational waves in 1916. He did it using his general theory of relativity, which is a theory that a set of laws of gravity and of warp space-time that he developed in 1915. So this was actually about 6 months after he had formulated the theory and his laws of general relativity that he made this prediction. And what he said is this, that if you have a gravitational wave that is propagating through the screen here toward you, then what the gravitational wave will do is it will stretch and squeeze space in the two dimensions that are perpendicular to the propagation direction, so in the screen. And you can see this stretching and squeezing of space by laying down a rectangular grid of particles. They're all at rest with respect to each other before the wave arrives. This is out in interplanetary space. There's no significant gravity from anything except the gravitational wave. And what the gravitational wave does is it pushes these particles together horizontally, squeezes them apart vertically, then pushes and squeezes in the opposite direction in this oscillatory sort of fashion. So just think of stretching and squeezing in that manner. And these particles are really markers for inertial reference frames, if I want to get a little bit technical. You imagine you have two inertial reference frames, one here and one there. When the gravitational wave goes by, the inertial reference frames are pushed together and apart, together and apart. That doesn't happen in normal physics, but in relativity, with this gravitational wave, it happens pushing the inertial reference frames back and forth relative to each other. That's what I mean by stretching and squeezing of space. In 1972, after I had become fascinated with gravitational waves due to experimental work by a man named Joseph Weber, who was at the University of Maryland, after I had learned about gravitational wave theory from John Wheeler and others, I sat down with some of my students, particularly Bill Press, who went on to be deputy director here at Los Alamos for a while. Bill and I laid out a vision for what you could do with gravitational waves for astronomy if gravitational waves could be detected. And the foundation for this vision for gravitational wave astronomy is the enormous contrast between electromagnetic waves that were at that time being used, the only main thing being used to study, to do astronomy, and gravitational waves. So electromagnetic waves are oscillations of the electromagnetic field that propagate through space as time passes. Gravitational waves are oscillations, in some sense, of the fabric of space-time, a stretching and squeezing of space as time passes. In astrophysics and astronomy, electromagnetic waves are almost always incoherent superpositions of emission from individual particles and atoms and molecules, whereas gravitational waves are emitted coherently by the bulk motion of large amounts of matter and energy. Electromagnetic waves are all too easily absorbed and scattered as they travel from their source to us. Gravitational waves are never significantly absorbed or scattered, not even if they were created in the Big Bang. They could bring to us an image of the Big Bang, birth of the universe. You could never get that with any other form of radiation. Gravitational waves are the only kind of radiation that is so penetrating that it can, and it will, I think, within the next few decades, start bringing us images of the birth of the universe. Because of these enormous differences between these two types of radiation, many gravitational wave sources will never be seen electromagnetically, and many will be seen electromagnetically, and the joint observations with electromagnetic telescopes and gravitational telescopes will be absolutely wonderful. And because of these enormous differences, we can expect that gravitational wave detectors will bring huge surprises. So that was the view that Bill and I had in 1972. And that was the same year as Ray Weiss described in a technical article that he circulated among his friends and he published in an internal report series at MIT, described a new type of gravitational wave detector. Now, Ray being Ray, believed you should not publish something like this until after you had built the instrument and detected gravitational waves. And so he didn't publish it in the open literature, he published it in this internal report series, but circulated among his friends. Of course, he would have waited 50 years to publish it in that case. And his new kind of gravitational wave detector is depicted here. You have 4 mirrors that hang from overhead supports. When the gravitational wave comes along, it pushes these 2 mirrors apart, while it's pushing those together because of the stretching of space in this direction, the squeezing of space in that direction. At the next half cycle, it pushes these apart and pushes those together. As long as the oscillations are fast compared to the 1 cycle per second normal oscillations of a swinging pendulum. At higher frequencies, it's as though these were free masses, free particles, instead of being suspended by wires. And so the idea was that you send a laser beam in, you split it in two at a beam splitter. The light went into the two arms, was trapped in here and in there for a while, and then the light comes back out, recombines, goes into the photodetector, and you use the interference of the light from the two arms to give rise to a signal at the photodetector, whereas the arms are stretched and squeezed, the light intensity of the photodetector goes up and down. So this is interferometry, laser interferometry. And this was the basic idea of Ray Weiss's gravitational wave detector scheme. Now, I heard about this, but I had not had a chance to really study Ray's technical paper. In the weeks as we were finalizing the writing of a textbook, John Wheeler, my PhD advisor, Charles Misner, another of Wheeler's former students, and I. And we were in the final few weeks of finalizing this textbook when I heard about this. And so I felt we had to say something about this idea in the textbook. And so there's a very brief few sentences in there that conclude with, this technique is not very promising. And why did I say it was not very promising? Let me give you some numbers. So here are the mirrors that may be, for example, 4 kilometers apart, was how far apart they ultimately are in our LIGO gravitational wave detector. And how big is the motion of the mirrors back and forth? Let's begin with 1 centimeter. Divide by 100, you get the thickness of a human hair, 100 microns. Divide by 100, you get the wavelength of light, 1 micron. This is the wavelength of the light that's being used in this interferometry scheme to detect the gravitational waves. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 1,000, you get the predicted mirror motions. Now, I looked at those numbers, and I said, Ray is either crazy or something. And so I just put it very mildly, it's not very promising. And then, from 73 to 75, I studied Ray's 1972 technical paper in great detail, started doing my own calculations about this scheme. I had long conversations with Ray and with others, and I became convinced that there was a real possibility that this could succeed. And having become convinced, because Bill Press and I had this vision for what you could do with gravitational waves, I decided that I and my research group of theorists should do everything we could to help Ray and his experimental colleagues pull this off. And so I spent then the rest of my career eating crow over what I wrote in this well-known textbook on relativity. So I'm going to compactify 40 years of effort on LIGO into 1 slide. What I'm going to do is simply show you into 2 slides. I'm going to show you key leaders in this, Ray Weiss, Ron Drever, whom we brought to Caltech to start an experimental effort in parallel with Ray's. Ray and Ron and I founded the LIGO project, co-founded it as a Caltech-MIT collaboration. Robbie Vogt, who was our first director, who led us in writing a very successful proposal to build LIGO, successful proposal to the National Science Foundation in 1989. Stan Whitcomb, who was the deputy director under Robbie, but then became chief scientist, and along with Ray Weiss, was probably the key intellectual leader on the experimental side of the effort. Barry Barish, who was the man who really made this succeed. He came on as our second director, and he organized us into a team that really pulled this off successfully. He made key technical decisions in the way that the leader of a large project does, by consulting with all of the stakeholders and all the most brilliant people who had input on the decision, and made key technical decisions. And he created the LIGO Scientific Collaboration, which I will show you in a few minutes. Then 2 other directors who followed on after Barry and were absolutely key to bring us to where we are today, Jay Marks and Dave Wrightsey. But the people who really pulled this off were the 1,200 scientists and engineers of the LIGO collaboration at 100 institutions in 18 nations. And this is what Barry built, beginning with the small groups at Caltech and at MIT. September 14, 2015, our second generation of detectors, the advanced LIGO detectors, were just preparing for their first gravitational wave search. As Tom said in his introduction, we went through 2 generations of detectors. We said when we made our proposal in 1989 it would take 2 generations to pull this off, and it did. We were 3 days in advance of starting the search, and the first signal came in. And Dave Wrightsey declared to the team, the search has started. The detectors were frozen in the configuration that they then were in, and we were off and running. And what was this first search all about? Well, I have lost a slide, a crucial slide. Let me just see what's going on here. I'm going to exit this and just look. I can't believe this is gone. It is gone. Okay. This is so important. I'm going to cheat. This has never happened to me before, but there's always a first time. So I go down to my lectures directory. I go into my, these are, we've got to get to 2019, Bucharest. Well, I'm not doing terribly well. Here we go. Oppenheimer lecture. I'm now going to go to my possible slides for this lecture. I'm going to dig out the slide that has somehow disappeared. You have to believe this is really important if I... Okay, we're getting down here. Okay. It's missing there too. No, it's not. Here it is. Okay, here it is. There are always backups. Anyway, I apologize. So can you turn the lights all the way off? What you're seeing here is the source of gravitational waves that we discovered on September 14 of 2015. These are 2 black holes. You see the black hole shadow against a field of stars. And this other black hole, you see the black hole shadow. You see a swirling pattern of stars created by a gravitational lensing. The story is this, that 1.3 billion years ago, in a galaxy far, far away, 2 black holes circled around and around each other, creating swirling patterns in the star field by gravitational lensing, and emitting ripples of warped space-time, that is gravitational waves. And as they lost energy of the gravitational waves, the black holes spiraled closer and closer and closer to each other, until finally they merged in a giant crescendo, a huge gravitational wave burst. Those gravitational waves then propagated out of the galaxy in which they were born into the great reaches of intergalactic space, across intergalactic space for 1.3 billion years. And 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals, this burst of gravitational waves arrived at the outer reaches of our Milky Way galaxy. For 50,000 years, they traveled through our galaxy, and on the 14th of September 2015, they touched down on Earth at the tip of the Antarctic Peninsula, as best our data can tell us. They traveled up through the Earth totally unscathed by all the matter in the Earth. They emerged first at the LIGO Gravitational Wave Detector in Livingston, Louisiana. And then 7 milliseconds later at the LIGO Gravitational Wave Detector in Hanford, Washington. They stretched and squeezed the mirrors in the corner and the ends of these vacuum pipes, those mirrors that were hanging in just the design that Ray Weiss proposed. And the signal from that then went out of the photodetector into a computer, and it was analyzed by the computer, pre-programmed computer, and the data then were put on a website, an internal LIGO website for members of the collaboration to look at. I had a telephone call from a colleague of mine, a young colleague, saying that go look at this particular web page, LIGO web page, we may have detected a gravitational wave. I went and looked at it, and it was too good to be true. I didn't believe it, because the signal was so perfect, and it was really somewhat stronger than I expected. And neither did most anybody else. We figured there had to be something had gone wrong, because the signal was so perfect. But these instruments are so complex. They have to be complex because there's so many things that can go wrong inside them. So complex that there are 100,000 data channels come out of them and out of the environment. And so the younger members of the team who really understood the details of the instrument went in and they looked at all of the data channels where there would be fingerprints of anything having gone wrong. And they looked, and there was no sign of anything having gone wrong. Then we worried, had we been hacked? It was somebody pulling a joke on us. But even the very best experimenters in LIGO, like Stan Whitcomb, could not hack without leaving lots of fingerprints. And there were no fingerprints, so we decided clearly we hadn't been hacked. And so the team published the result. And it made front page headlines in all the major newspapers and a lot of the minor newspapers around the world. And a few days later, Ray Weiss was on a subway in New York City, and he took this photograph. This is not a cartoon, this is a photograph. Well, that his, I guess it was his brother-in-law took. It says, "Scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet." And the day after the announcement in the New Yorker, there appeared this cartoon. What you have to understand is that if you put the gravitational wave signal on a loudspeaker, it goes whoop, in what we call a chirping sound. One bird says to the other, was that you I heard just now, or was it two black holes colliding? So this became part of culture very, very quickly. And it was just amazing how quick that happened. By the August of 2017, so this is after 2 years, we had done 2 gravitational wave searches with these instruments. And we had seen 10 colliding black holes, and here are the simulations of those 10 colliding pairs of black holes. Some of them are big, some of them are small. They range in masses from something like 80 solar masses down to something like 8 solar masses. Just a wonderful range of black hole pairs that we had seen merge. LIGO then, at that time, had seen 10 black hole collisions and 1 neutron star collision. I'm sorry, I'm now off of this, and I got to go back to my original talk. So those are my possible slides. Now I'll get back in here to where I am here. Okay. So we saw 10 binary black hole collisions, black hole collisions in the first 2 searches as of August 2017. Could you turn the light down now again? And these are them going around each other. And we had located these sources of the gravitational waves, these black holes on the sky. This is just the sky imprinted on the surface of a black sphere. But the primary way that we determine the direction to a source is by the delay in the arrival time of a piece of the signal at 2 or 3 different locations. I told you that the signal arrived first in Livingston, Louisiana, and 7 milliseconds later in Hanford, Washington. So the source was obviously in the south because Livingston is more or less south of Hanford. It was down, as I say, near the Antarctic Peninsula. That was the direction of the source. And so these are the signals, the locations of the signals on the sky as determined by the LIGO detectors, but there are just 2 detectors, and so we could only get good north-south accuracy. We could not get good east-west accuracy. There's one very small, much smaller error box for one of these sources, the source GW170814, which the waves came in on August 14th of 2017. And the reason that we had suddenly a much better error box is a 3rd gravitational wave detector joined our search, put together by a team called the Virgo team, that is a collaboration of France, Italy, Poland, and the Netherlands. Here is a photograph of the corner station of the Virgo detector. And so that gave us much better accuracy. And that was crucial a few days later when we saw gravitational waves from 2 black neutron stars that collided. Each of these neutron stars, and I remind you, Robert Oppenheimer was the first person to do a mathematical model to work out the structure and the properties of neutron stars. Each of them is about 20 kilometers across. Each of them weighs about 1.5 times what the sun weighs. And they're going around and around each other, emitting gravitational waves as they circle and spiraling together as they lose energy of the gravitational waves. And they come crashing together and produce a gigantic fireball of hot nuclear matter that goes flying out through the universe, radiating very strongly in every form of every wavelength band of electromagnetic radiation that there is. This is what is called by theorists before it was seen a kilonova. Here is the gravitational wave signal as seen in the three different detectors, the 2 in the US and the 1 in Europe, plotted in a manner I'm not going to explain. But the key thing is that 1.7 seconds after the neutron stars collided, there was a burst of gamma rays. That's the highest energy form of electromagnetic radiation that astronomers use. And the gamma ray satellite, the Fermi gamma ray satellite, said that the signal was coming from this region. That's the LIGO and Virgo error box. So it coincided, although it had much worse angular accuracy, the gamma rays. It did overlap with the LIGO-Virgo error box. Then, over the next few hours, each form of radiation with longer and longer wavelength was seen: X-rays, ultraviolet, optical, infrared, and radio waves. This was the most studied object or event that astronomers have ever seen. Something like 1/4 of all of the astronomers in the world studied it with one type of telescope or another. And then we call this multi-messenger astronomy. We think of gravitational waves as one messenger: X-rays, gamma rays, radio waves. These are all messengers. And one among the very interesting results that came out of this was from observations of the electromagnetic waves. It was verified, a prediction that theorists had made, that huge amounts of gold and platinum were created through nuclear fusion in the collision of those 2 neutron stars. That in fact, it's likely that almost all of the gold and platinum that you see here on Earth, almost all of it in the universe, is created in neutron star collisions. So this is an example of a great discovery made through multi-messenger astronomy. Our third gravitational wave search began on April 1, that's just a month ago, with improved detectors. You can now get onto your smartphone an app called Gravitational Wave Events. It's been available for a while for the iPhone. I think it's just coming out about now for Android phones. And you go on there, and inside that app, you see a page here that lists gravitational wave signals that have come in. And let me walk you through these signals. So on April 8th, there's a signal. You go in and you look at the details, and you have there the observational data from LIGO and from all the electromagnetic telescopes that went and searched for it. And it was concluded this is 2 black holes colliding on April 8th. April 12th, another pair of black holes collided. On April 21st, there was a signal that was really quite weak, but with 97% probability, it was a pair of black holes colliding, 3% probability that it's some sort of terrestrial noise. On April 25th, 2 neutron stars collided to produce this, but one of the LIGO detectors was down, and so the accuracy of the error box of where this is on the sky was lousy. And the electromagnetic astronomers are having a terrible time identifying where it is because we didn't have all 3 detectors operating at that time. But you can follow on this app in real time as the data come in from all the telescopes. And on April 26th, there was a signal that again is fairly weak. But if it's real, it is very likely a black hole tearing a neutron star apart, but it might be 2 neutron stars colliding. This could be our first observation of a black hole tearing a star apart. And then on May 3rd, just a few days ago, another signal from 2 black holes colliding. And it's really wonderful. Just go in this and watch in real time as the astronomers make these discoveries, and gravitational wave astronomy becomes an everyday phenomenon. I want to conclude by talking about the storm in the fabric of space and time that is created when 2 black holes collide. So the first black hole collision that was observed on September 14th of 2015, physicists who solve Einstein's equations on computers, this is called numerical relativity, a team called the SXS team that I co-founded together with Saul Tukulski, who's at Cornell University, as a former student of mine. This team then, knowing, we knew what the signal was. It is a signal that comes from 2 black holes. One weighed, I have to remember, one was about 30 solar masses, the other was about 29 solar masses, I forget precisely. But knowing by comparing the simulations with the observations, comparing the shapes of the waves in the simulations with the shapes of the waves in the observations, we can conclude what the source was, and then the simulations show you what the collision would have looked like as seen from a higher dimension. And so here you have the 2 black holes going around and around each other. The color coding is a slowing of time. You see the funnels in the shape of space, and you see a huge splash, like in a storm at sea. A gigantic splash at the moment of the collision. Stop the moving momentarily then, and then it oscillates and the signal dies out. That collision, as seen from a higher dimension, you can turn the lights back up, that created gravitational waves that carried off 3 solar masses of energy. It's as though you had taken 3 suns and annihilated them and turned all of that energy into gravitational waves. And that happened so fast, in about 1/10 of a second, that the power output, the energy per unit time, was 50 times larger than the power output of all the stars in the universe put together for just 1/10 of a second. This, then, and other black hole collisions like it, these are the most powerful explosions, most powerful events that we have ever seen, we humans, aside from the evidence of the Big Bang birth of the universe. And no electromagnetic waves have been seen at all, just gravitational waves with this enormous 50 universe luminosities of gravitational wave power. This movie captures only a small portion of the space-time storm created by the black hole collision. We call this geometric dynamics. And I'm going to wind up by telling you a little bit more about the space-time storm and what happens to these vortices of twisting space that stick out of each black hole when the holes collide. So I'm going to take 2 black holes. They're going to, for simplicity, collide head-on. One of them has a clockwise vortex of twisting space pointing up, counterclockwise down. This is counterclockwise up and clockwise down. These are vortex lines that guide the twisting space up here and down there. So I'm going to just show you through color coding the form of the vortex that's sticking out of the black hole. A blue vortex here, red on the backside of the black hole, a red vortex here, blue on the backside of the black hole, vortices of twisting space. And let's watch the collision start. And what you see here now is the horizon of the black hole, the point of no return. You go through there and you can't get out. You now have 4 vortices sticking out of this black hole. It turns out black holes do not like to have 4 vortices. They only like to have 2. And when they settle down into a quiescent state, they can only have 2 vortices left. And so what happens, these vortices robustly retain their individuality. And here's what happens. So watch, there's a blue vortex up here on the upper right. Collision, the blue vortex has become red. And as the black hole vibrates, it's blue, it's red, it's blue. These vortices are fighting with each other, and as they fight, they exchange vorticity. What was a counterclockwise vortex becomes clockwise as it fights with its reverse pair. And so here is a more detailed explanation. At the moment when you see blue here and red there, you have a vortex of twisting space, a red vortex, that goes out of that red spot and into the red spot on the backside. A blue vortex goes out into the blue spot on the vortex, clockwise vortex and counterclockwise vortex. When this goes green during the pulsations, those vortices pop off. They embrace each other according to the simulations of our SXS team, and they create smoke rings of twisting space that travel outward into the universe. And as a vortex of twisting space in the form of this ring travels outward, the motion of these vortices creates what we call tendices. These are the pieces of space that stretch and squeeze. So there's a stretching along this small ring of that torus, and there's a squeezing along this big direction along that ring. And so you have then these embraced vortices of twisting space, tendencies of stretching and squeezing space, traveling out into the universe, and that's what a gravitational wave is. We had no idea that this was how warp space-time behaved in a storm. We saw it in these simulations of colliding black holes. 400 years ago, Galileo built a small optical telescope, pointed at the sky, and discovered the 4 largest moons of Jupiter. 4 years ago, the LIGO team had its advanced detectors beginning to operate and saw gravitational waves from colliding black holes. Galileo, 400 years ago, with his optical telescope, created electromagnetic astronomy. LIGO created gravitational astronomy. From gravitational astronomy now, we have already seen how we can explore wonderful things about black holes, about colliding neutron stars. But when you think of the huge revolution in our understanding of the universe that has come from electromagnetic waves since Galileo's time, 400 years ago, I invite you to speculate about what will be discovered about the universe, what kind of revolutions there will be in the next 400 years from gravitational wave astronomy and electromagnetic astronomy working hand in hand. Thank you.
Thank you so much, Professor Thorne, for that fascinating talk and for explaining to us what black holes really are and where we have come today in our understanding. I have no doubts that if Robert Oppenheimer were sitting in the front row, he would have no need to stand up and say, "Let me explain what the lecturer is speaking about." So thank you again. It is the committee's tradition to present our distinguished speakers with a bronze medallion inscribed with their name and their lecture date. This commemorative medallion was designed by the late Santa Fe artist Una Hanbury and is adapted from a bust of J. Robert Oppenheimer that Hanbury executed in 1973. Only 3 casts of the bust exist. One commissioned by Los Alamos National Laboratory and on display at the laboratory's J. Robert Oppenheimer Study Center. The second was commissioned by the Smithsonian Institution's National Portrait Gallery. And the third and final cast of the full bust was obtained by the committee and is on long-term display at the Los Alamos History Museum. It is from this bust that the commemorative medallion was adapted and features the profile of J. Robert Oppenheimer. At this time, on behalf of the J. Robert Oppenheimer Memorial Committee and as chair of the committee, it is my pleasure to present this commemorative medallion to you, Professor Thorne, and thank you for joining us tonight as our distinguished speaker. I would now like to invite everyone for a reception in the Dwayne Smith Extended Lobby, just to the left as you exit the auditorium. Thank you again, Professor Thorne, and thank you all for attending our memorial lecture.